I wired 400 car batteries together. This is what 160,000 amps looks like. There are moments in human history when a person looks at the laws of nature, and instead of saying, I should respect that, they say, but what if I put 400 of them together? Tonight's story begins with one of the most gloriously unreasonable sentences ever spoken in the English language. I wired 400 car batteries together. Not one battery, not two, not the kind you use to jumpstart your cousin's Toyota when he insists it's just the alternator, even though smoke is coming out of the hood like the car is choosing a new pope. No, 400. And the result, according to the experiment that inspired this idea, was a setup capable of roughly 160,000 amps, a current so absurd that even people who understand electricity professionally tend to respond with the same technical phrase, absolutely not. So tonight, we are going down the rabbit hole. We are going to talk about batteries, current, magnetic force, molten metal, arc flash, and why electricity is one of the few things in the universe that punishes arrogance instantly. And we are going to do it like explorers standing at the edge of a glowing crater, asking the oldest scientific question of all: what happens if we touch it? The beautiful stupidity of scale. A single car battery is so ordinary you barely think about it. It sits there in your vehicle, under the hood, quietly waiting for the moment your engine needs to wake up. It is not glamorous, it gets no applause, nobody posts cinematic montages of their battery. Nobody leans out of a Lamborghini and whispers, "Check out the lead-acid chemistry, baby." And yet, the humble 12-volt car battery is a brute. Typical automotive batteries are often rated in the several hundred cold cranking amps range. Many common models land around 500 to 800 CCA, with some examples around 800 CCA. CCA measures how much current a battery can deliver for 30 seconds at 0 degrees Fahrenheit, minus 17.8 degrees Celsius, while maintaining a specified voltage. In plain English, this is a box of acid and lead specifically engineered to dump an outrageous burst of current into a machine with controlled violence. Now imagine taking that ordinary violence and multiplying it by 400. That is when the story stops being car maintenance and starts becoming Dr. Frankenstein opens an AutoZone. The experiment widely discussed online this year centered on exactly that, a giant battery bank built from 400 car batteries with current claims in the neighborhood of 160,000 amps. That figure is what makes people's eyebrows leave their bodies and relocate permanently into the upper atmosphere. Because voltage gets all the fame. Voltage is dramatic. Voltage sounds dangerous. Voltage has branding. But current? Current is the part that shows up with a shovel. Voltage is pressure. Current is flow. You can have a system with high voltage and low current. You can have a system with modest voltage and monstrous current. And when people hear only 12 volts, they sometimes make the fatal mistake of translating that to safe. No, my friend. A car battery bank wired mainly in parallel does not dramatically raise the voltage. What it raises is the available current and capacity. That is the entire point of parallel battery configurations. Voltage stays the same, but amp-hour capacity and current delivery rise. So if one battery is a horse, 400 batteries in parallel are not a slightly stronger horse. They are a stampede wearing copper shoes. And here's where the rabbit hole gets deeper. When a lead-acid battery is shorted, it can deliver extremely high current. Engineering literature has described shorted lead-acid batteries as capable of producing 100 to 1,000 times their typical discharge current. In other words, these things are civilized only under normal use. Under fault conditions, they revert to ancient barbarism. So the real question is not, can 400 car batteries make a lot of current? Of course they can. The real question is, how do you stop that current from instantly turning your experiment into a welding accident hosted by Zeus? The switch problem, Or how do you turn on a small sun? The average person thinks the hard part of a giant battery experiment is gathering the batteries. Wrong. The hard part is the moment you try to connect them. Because when current wants to move, it doesn't politely knock, it lunges. And at these scales, a normal switch is not a switch, it's a future fossil. Reports around the experiment describe the creator building a massive custom switching mechanism because this level of current is far beyond what ordinary off-the-shelf hardware is meant to handle. That's exactly what you'd expect. At very high DC currents, connection resistance, contact design, and busbar geometry become everything. Even tiny resistance turns into colossal heat. This is one of the most important principles in electricity. At insane current, tiny imperfections become dramatic events. A little resistance, that becomes heat. A little loose contact, that becomes arcing. A little bit of optimism, that becomes a headline. Because power loss follows the famous rule I squared times R, current squared times resistance. Not current times resistance, current squared times resistance. And that squared part is nature's way of saying you are no longer in the beginner zone. Double current and heating doesn't double, it explodes upward by a factor of 4. At 160,000 amps, your mistakes are no longer mistakes, they are special effects. What 160,000 amps actually looks like. Now, let's answer the title question. What does 160,000 amps look like? It looks like metal forgetting that it was ever solid. It looks like copper behaving less like infrastructure and more like pasta dropped into boiling water. It looks like magnetic fields flexing hard enough to physically shove conductors around. It looks like the laws of electromagnetism stepping out from behind the curtain and saying, "Did you think I was theoretical?" Because current doesn't merely heat things. Large current creates large magnetic forces. This is where it gets truly cinematic. When enormous current surges through conductors, each conductor creates a magnetic field. Those fields interact. The mechanical forces can become violent enough to bend, jerk, or even destroy hardware. That's one reason high fault current systems are engineered with such obsessive attention to bus bars, supports, clearances, and protection. So when you see giant current experiments melting springs, crushing thin metal, or producing violent electromagnetic effects, that's not magic. That's Maxwell's equations taking off their reading glasses. And the craziest part, people often imagine electricity as invisible. But at the extremes, electricity becomes extremely visible. It glows, it spits, it screams, it vaporizes metal into plasma. It turns air itself into part of the event. Electricity begins as an abstraction in a textbook and ends as a weather system in your garage. Why this is so dangerous? Now, let's get serious, because this is not a try-this-at-home story. This is a please don't turn your backyard into an OSHA study story. Short-circuit-capable battery systems are dangerous for a few reasons. First, the fault current can be enormous. Battery industry and engineering sources note that short-circuited lead-acid systems can deliver extremely high current, depending on internal resistance and connection resistance. Second, high fault currents can create arc flash conditions. NFPA notes that arc flashes can produce extreme temperatures exceeding 35,000 degrees Fahrenheit, 19,400 degrees Celsius. That's not poetic exaggeration, that's professional safety guidance. Third, lead-acid batteries involve chemical hazards too. Acid, gas, heat, exploding fragments, molten metal, shrapnel, the whole what if a chemistry set learned violence package. So when you hear 400 car batteries, don't picture a bigger jump start. Picture a machine sitting uncomfortably close to industrial fault conditions. That's why these experiments fascinate us, not because they're safe, not because they're normal, but because they pull back the curtain on how much power hides inside everyday objects. Your car battery is mundane only because it's usually contained inside a system designed to behave. Take away the rules, and the battery reminds you it belongs to physics, not convenience. And this may be where the story becomes bigger than one mad experiment, because humans have always wanted to catch lightning. Before modern batteries, we used static electricity, Leyden jars, primitive cells, and whatever else we could build from curiosity, metal, and a suspicious disregard for eyebrows. Electricity has always occupied a strange place in the human imagination. It's invisible but undeniable, abstract but brutal, silent until it isn't. It feels almost supernatural until you understand it. Then you understand it, and somehow it becomes more terrifying. Because mystery is scary, but measured power is scarier. A ghost in the attic is one thing. A quantified 160,000 amp discharge is another. The ghost might be fake. The current is extremely real. And that's why experiments like this go viral.
Not just because sparks are cool, and sparks are cool, let's not lie to ourselves, but because they awaken something ancient in us, the desire to see the invisible forces of the universe become visible, to see equations become flame, to see theory become motion, to see nature stop being a paragraph and become an event. That is what science is at its best. Not just information, revelation. The comedy of human confidence. There is also something deeply funny about the entire premise. Somewhere, at some point, a man stood in front of a growing mountain of used car batteries and said, "Yes, more." That is the kind of confidence that built civilization. Also the kind of confidence that made warning labels necessary. You have to admire it, because science often advances through a very awkward emotional sequence. Curiosity, calculation, questionable confidence, unexpected noise, learning. And the internet has given us a front row seat to this process. Once upon a time, if a person wired hundreds of batteries together, only a few horrified neighbors would know. Now, the whole world gets to watch, which is beautiful, because science education has always had two great teachers, the textbook and the guy who clearly should not be doing that. One explains the principle, the other burns it into your memory. The physics behind the spectacle. Let's pull the rabbit hole into one clean trail. Why can 400 car batteries deliver absurd current? Because when batteries are wired in parallel, the voltage stays the same while the capacity and available current increase. Why doesn't only 12 volts mean safe? Because danger in these setups comes heavily from fault current, heat, arcing, and the energy dumped through low-resistance paths. Why do things melt so fast? Because resistive heating scales with I²R. With very large current, even tiny resistance turns into huge heat. This is why contacts, conductors, and switch design matter so much. Why do conductors move or deform? Because high current creates strong magnetic fields, and those fields exert forces on nearby current-carrying conductors. Why is arc flash such a nightmare? Because electrical arcs can generate extreme heat. NFPA cites temperatures over 35,000 degrees Fahrenheit, along with blast pressure, molten material, and severe injury risk. So the giant battery bank experiment is not fascinating because it is random. It is fascinating because it is a concentrated, theatrical demonstration of laws that already govern power systems, vehicles, substations, and industrial safety. This is not fake drama. This is real physics at the point where it starts looking mythological. The moral of the story. There is a lesson here, and it is bigger than batteries. Modern life makes power feel ordinary. You flip a switch, the room lights up. You plug in a charger, your phone drinks from the wall like a tiny electric vampire. But behind every convenience is a force that does not care about your confidence. Electricity is obedient only inside systems of discipline. Proper insulation, proper spacing, proper switching, proper fusing, proper design. Proper respect. The moment you remove respect, electricity stops being your servant and becomes a reminder. a reminder that the universe runs on laws, not vibes. And that may be the most important thing science teaches us. Not merely how powerful nature is, but how precise. You do not negotiate with Ohm's law. You do not persuade arc flash with good intentions. You do not tell 160,000 amps, "Be gentle, I'm learning." No, you learn the rules, or the rules introduce themselves. So what does 160,000 amps look like? It looks like glowing metal. It looks like violent magnetic force. It looks like a machine trying to become a thunderstorm. It looks like ordinary car batteries dropping their disguise and revealing that they were little boxes of stored fury all along. And maybe that is why we cannot look away. Because buried inside the familiar world, inside a hood of a car, inside a cable, inside a battery terminal, is enough power to humble us, teach us, and, if we are wise, fill us with wonder. The universe is not only stranger than we imagine, sometimes it is wired in parallel. And if you enjoyed this descent into the electrified abyss, subscribe, because next time we're going even deeper into the physics of arcs, plasma, and the beautiful moment when human curiosity shakes hands with danger and says, "Just one more test."